before. And yeah. So I'm just going to fill these in. I want to turn these into summation notation, and also talk about the radius converters of each one. So just because I forgot to hit record before, this first one, this was just all the coefficients were 1 over n factorial. So let me just write this again for the sake of posterity. So that was sum of x to the n over n factorial. Now sine x, right? So you guys got the alternating odd powers with factorials on the bottom, right? So one question is how to turn this into summation notation. So we want this to be the sum from n equals 0 to infinity of something. And so we clearly have an x. We clearly have a something factorial. We clearly have a -1 to some power. So we got question mark here. So right, I'm just saying like the general structure is something like this, right? But how do we encode the odds? Somebody was saying it. How do we encode the odd powers? Anyone? Yeah, we use 2n plus 1 for odd numbers, because when you plug in 0, you get 1. When you plug in 1, you get 3. When you plug in 2, you get 5, right? So this is right here is 2n plus 1. That's just a nice way to encode the odd numbers. I mean, 2n encodes the even numbers, right? If you just think about the sequence 2n for various values of n, you get 2, 4, 6, 8, 10. So adding 1 shifts it to the odd numbers. And then the denominator is the same as the exponent, right? So it's 2n plus 1 over 2n plus 1 x to the 2n plus 1 over 2n plus 1 factorial. But there's a -1, and it turns out I think that this is just supposed to alternate plus minus plus minus. So it actually n just works here, because when you plug in 0, you get -1 of the 0, which is 1. When you plug in 1, you get -1 of the 1, which is -1. So that turns out to be this. It looks kind of terrible, but it's really just a way to encode the odd powers and the alternating nature of this. Does that seem? Again, once you write down a potential summation notation, you can always write out the first few terms and see if it matches, right? And if not, you can tweak it. Does that make sense? Are we good? Okay, it turns out because of the factorial nature here that, again, r equals infinity. So this actually converges everywhere. Again, so we actually saw this with the cosine x. The cosine x is going to be very similar. We saw the cosine x we saw those graphs going back and forth, getting closer and closer to cosine, right? So how do we encode this one then? Summation notation. What do you think the difference is between this one and the other one? What should we have instead of 2n plus 1? Just 2n, right? Because we're doing even powers, right? So -1 to the n times x to the 2n over 2n factorial. Okay, and again, r equals infinity. So this actually converges everywhere, which is amazing. So e to the x, sine x, and cosine x are these really nice ones that converge everywhere. And actually, they look kind of similar too. It actually turns out there's a very nice connection among those three, because this is like the odd even terms, that's like the odd terms, and this one's like all the terms. It'd be nice if you just added these together and got that, but you don't because of the minuses. I'll come back and talk. There's something cool there that I'll talk about. Okay, this one, natural log. So now, well, we're dividing, it's kind of clearly x to the n over n, right? Except it's alternating. And we need to start at 1 because we don't want to divide by 0. And then We could try -1 to the n here, but that's a problem, right? Because if I plug in n equals 1, I get a negative. It would start out -x. If you plug in n equals 1. So in fact, this should be like -1 or +1. Can't remember what the convention is. I'll just say -1. So it's -1 to the n minus 1 times x to the n over n. Over n, like that, right? But natural log has a nice Taylor series. It's kind of similar to the e to the x one, but without the factorials and with the alternating. Here, when you do the ratio test, you're basically going to have an n plus 1 over n in the ratio test. I think you guys have done enough ratio tests with power series that you can kind of see where I'm going with that. Like the x to the n plus 1, x to the n will cancel. These don't matter because you take the absolute value, n plus 1 over n. So it turns out the radius here is 1. And I'll show you in a minute an example of this. So it turns out that this only works from -1 to 1. And there'll be good, okay, we're gonna come back and talk about that. I just wanna finish filling in some of these. So this one, the coefficients worked out very nicely, right? To just be plus or minus 1 each time. So this is the sum of 0 to infinity of -1 to the n times x to the n. It's actually geometric with -x. You're multiplying by -x each time. So you could write it as -x to the n if you wanted. Yeah, so yeah, and then the radius here, actually this is the one I think I want to show you. Maybe the radius is 1. A lot of these have radius 1 actually. This one is nice. This one is just the sum 0 to infinity n plus 1 times x to the n. I think the coefficient is 1 more than the power. So that's the way to encode that. Unmute my microphone on the Zoom. Let's hope I did. Okay. Yeah, right. The coefficient is 1 more than the power each time. 2x to the first, 3x squared, 4x cubed. So if you make this x to the n, this has to be n plus 1. Does that make sense? Okay. And again, it turns out r equals 1 here. Okay, so let me just show you a picture of this for a second. Let me see, I'm gonna have to, or do I have the Mathematica code download somewhere already? I think I probably should. Sorry, I'll pull the screen up in a second. Yeah. Oops. And I'll share screen. Oh. Okay, let me share screen. Fun. Okay, so this is that thing that we had done before. Where really, look, actually, you can see the cosine. This really is the expression that we came up with for cosine, right? And this was trying it for different values of d, for different stopping. So this is not the Taylor series, these are Taylor polynomials. But as you increase the power in the Taylor polynomial, they really should all be integers. Oops, that's not what I don't want that. I wanted to just go through 6. Anyways, so you get these. It's really just doing the integer values, right? So this is, it's stitching itself along the cosine graph, and it just gets better and better as the power gets larger and larger. And it's still being good. You know, now it's on all the way from -20 to 20, and it'll keep going forever, which is what the r equals infinity means there. It's like, it really stitches itself along the graph of cosine x forever. Okay. But if you try 1 over, let me just do 1 over 1 plus x. Sorry. Sometimes I do that and sometimes I do that. So this is, so we just said that's minus 1 to the n times x to the n, right? That's number 4 right there on the board. Oh, what I do? Okay, so now if we start building the Taylor polynomials right to the 10th degree. What if I did this? It would slow down. Hold on. Oh yeah, you can see it stitching along, but notice what's happening near 1. You see it's bad, it's like not getting better. Do you see how that's different from the previous one where it would keep getting better and better, farther and farther along the graph? But this one is not getting better and better past 1. And that's really because the right-hand side, the Taylor series, diverges for x greater than or equal to 1. If I try to plug in like, 2 into this, we just get something that's getting bigger and bigger, and so it's going to diverge. So it can't possibly work past, it's centered at 0 and the radius is 1. So from -1 to 1, it's a good estimate. But past 1, it doesn't work. And in fact, you can sort of see why. You can almost see why the radius has to be 1. Sorry, I was going to stop the share, go back to the board. So, yeah, so this equality is only true for x between -1 and 1, actually strictly between -1 and 1. Right, that's what the r equals 1 means. And I think it makes sense because what happens at -1? What happens to the left-hand side at -1? What do you get on the graph when you plug in -1 here? There's a name for that. Somebody say it. It's an asymptote, right? There's a vertical asymptote here. I guess you can't really see it, but there's a vertical asymptote at -1 because it blows up, right? That's why it comes back up down from on the bottom left, the function. So it actually makes sense, like this can't converge because the function has a bad point at -1, so it better not converge past there anyways. So I think that's like, it's sort of like because makes sense because of the vertical asymptote at x equals -1 for 1 over 1 plus x. Right, that it's basically not going to converge past that point. But then because of this we've seen this with power series, that they converge equal and opposite from the center. So that's kind of why it breaks down past 1 also, because it's kind of symmetric. It only works a certain distance from each. So when it runs into that bad point is when it stops converging. Does that make sense? Okay. Now, natural log, by the way, has the same thing. Natural log is bad when x is -1. For this natural log of 1 plus x, right? Because you get natural log of 0. There's a vertical asymptote there also. So that's also a similar argument why the radius should only be 1 for this. Okay, now, so those are some of the famous ones we should know. I do want to talk about some of these other ones though, because some of you guys did e to the 2x, right? So a few groups got e to the 2x. So what happened with e to the 2x? The groups who got it, what did you guys have it over there? So you got 2 to the n over n factorial, x to the n, right? So this turns out to be, right, 1 plus 2x plus 4x squared over 2 factorial plus 8x cubed over 3 factorial plus 2 to the 4th, x to the 4th over 4 factorial. So if you do the table and the pattern, that's what you start to see. But do you notice something? I could rewrite this. 1 plus 2x. 4x squared is the same thing as 2x quantity squared. 8x cubed is the same thing as 2x quantity cubed over 3 factorial. 16x to the 4th is the same thing as 2x quantity to the 4th over 4 factorial. So I think there's something important here that may not be jumping out at you yet. Like, what if I just cover these up? Like, what does that look like? 1 plus blah squared over 2 factorial plus blah cubed over 3 factorial plus blah to the 4 over 4 factorial. We have something like that on the board, right? Sorry, let me just, we have it right here, right? So what's the difference between the Taylor series for e to the 2x and the Taylor series for e to the x? How do we turn the Taylor series for e to the x into the Taylor series for e to the 2x? What are we doing? You guys see where I'm going with this? We're just replacing x with 2x. So in fact, once you have the Taylor series for e to the x, you don't have to rederive the Taylor series for e to the 2x. You just replace x with 2x everywhere. And that's actually really cool. That's like a big thing here, which is like, so we actually don't have to, we didn't have to do the table to do the table. We know, like, let me just use a different variable. We know e to the u is 1 plus u squared over 2 factorial plus u cubed over 3 factorial plus u to the 4th over 4 factorial, et cetera. And then now just set u equals 2x. E to the 2x is 1 plus 2x plus 2x quantity squared over 2 factorial plus. So that's what I'm saying is, like, you can actually piggyback. There's all this piggybacking off of known Taylor series that we do. That's better than trying to make the table and find the pattern. Does that make sense? Like when you got to number 6, you could have just said, oh, let's just replace x with 2x in the formula for e to the x, and we were done. Does that make sense? Becomes even more relevant in number 7, because you guys got it. I think the only group that got to number 7. And what happened when you started trying to differentiate cosine of x squared? Well, the first one wasn't too bad. It's just a chain rule. Sorry for the camera, but basically what you see is that the board becomes a horrible mess, because you've got all these product rules and chain rules, and it compounds on itself, and it gets worse and worse, right? So if you try to do cosine of x squared with the table, it's horrible. And you guys got some numbers, but I think I know they're wrong because we'll see the easier way, right? So let's just try this with, this is the big upshot I want to talk about, is that, like, this is not bad. This is, yeah, cosine. So let's look at cosine of x squared. We know, again, cosine of, like, u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial. My u's and my 4's don't look too alike. Minus u to the 6th over 6 factorial. I mean, these are the patterns you should just beat in your head. Like, again, if you want to be an educated Renaissance person, you should know the Taylor series for e to the x, sine x, and cosine x. But now we just replace u equals x squared. set u equals x squared, and what do you get? You get cosine of x squared is 1 minus x squared squared over 2 factorial plus x squared to the 4th over 4 factorial minus x squared to the 6th over 6 factorial, and so on, which is really just 1. And then we can simplify these numerators. X to the 8th. So you actually only get multiples of 4 powers. So that really means that the third, like it really means the first, second, and third derivative of this function at 0 should be 0 because there's no coefficient, right? Because that's how you compute the coefficients, is finding the derivatives. And the first time you should get a non-zero coefficient is at the 4th derivative. So I don't know what happened over here. Well, I think you guys just plugged in wrong because sine of 0 is 0, and then there's a 0 there. So this is just 0. So that's 0. So this is 0. So you could see, like, if you went down and did this right, it's horrible. But so that's actually funny because in some ways, this is the wrong way to go with the problem. Like you guys aren't supposed to know that. I wanted to show you the pain of it so you can see how nice it is to just do this. By the way, there's some other kind of questions I can ask, which I think are kind of nice, which is like, what is so if f of x is cosine of x squared, what is f of like 73 of 0? Like, what's the 73rd derivative of cosine of x squared at 0? If I asked you this problem before, I could have asked you this in Math 1600, right? I could have asked you this after Calc 1. Problem is you'd have to differentiate this 73 times, plug in 0. So this would be, and then as you see, the derivatives get horrible. There's no nice pattern like with, I mean, if I just did it with cosine, it's not that bad, right? Because there's a pattern in the derivatives of cosine. But for this one, it's horrible, but you can answer it immediately, right? It's 0 because you can see it's going to skip 73, right? 73 is on multiple of 4, so it's going to skip 73. So in fact, the answer is 0. 0, not 0 factorial, 0. If I said the 70, well, what if I said the 16th derivative? So the next term is going to be what? Sorry? Yeah, so it'll be x to the 16th over 8 factorial. So here the coefficient of x to the 16th is 1 over 8 factorial, right? Plus 1 over 8 factorial. But we also know that, but also the coefficient equals the 16th derivative at 0 over 16 factorial. Right, just by definition, like that's, or by the Taylor series construction. So you can set these equal to each other to find the 16th derivative at 0. And it's actually a big number. If you look at it, it's going to be, let me, you see what I'm doing though? Like you can kind of, you can find out the derivatives of ugly functions this way, at least at certain points, if you know the Taylor series at that point. It's kind of neat. And there'll definitely be some questions like on the homework about that. That you can just sort of read off derivative information if you know a Taylor series. Might have even been a question like that on the, I can't remember, on the homework. But let's just kind of see, like, I'm just showing you that like there's all these ways to get information without having to do the long way. So just to finish off this thought, so, you know, this is the 16th. Like, because we can read the coefficient from knowing what the Taylor series is, but we can also tell that this should be the coefficient of x to the 16th by definition, by construction. And so that means the 16th derivative at 0 is actually 16 factorial over 8 factorial, which is really it's really 16 times 15 times 14 times 13 times 12 times 11 times 10 times 9, because the 1 through 8 cancel out. Who would have guessed? If you differentiate cosine of x squared 16 times and plug in 0, that's the number that you can. There's no way to do that direct. I mean, it's just horrible if you try to do that directly. I could ask Mathematica or something to do that. Like, it would do that pretty fast, actually. Except there's probably like 2 to the 16th terms or something in the derivative. Does that make some sense? Like, I'm just saying that you can actually glean information. Okay. Okay, last thing that I want to say, just because it's like kind of along the same lines. Like, so that's a big thing. Once you know Taylor series, the next big thing is like constructing other Taylor series from known Taylor series. That's kind of what we did with the cosine of x squared. That's what we did with e to the 2x. I claim you can do the same thing with like these like all three of these. So like, let's go back to like 4, for example. 1 over 1 plus x, right? Fuck, this is the clock, right? Okay, I've still got a couple minutes. So we know the geometric series formula. We usually use R, but if we have 1 plus x squared plus x cubed plus so on, if that converges, remember it's a over 1 minus r. So that's 1 over 1 minus x. This is really only true for x between -1 and 1. Right? So normally what we do is we think about the left-hand side and converting it to the right-hand side. But here, if you think about Taylor series, you could also think of this as the right-hand side as a function, and the left-hand side is its Taylor series. So this is the Taylor series for 1 over 1 minus x. That's another famous one you should definitely know, because it's really just the geometric series formula interpreted in a slightly different way. And then now think about 1 over 1 plus x. I can rewrite that as 1 over 1 minus negative x, right? And so it's that same u substitution sort of thing, or I can just replace x with negative x everywhere. So I can use this formula and say that, well, that's the same thing as 1 plus negative x plus negative x quantity squared plus negative x quantity cubed plus negative x quantity to the 4th, and so on, right? And that's 1 minus x plus x squared minus x cubed plus x to the 4th. So that's what you found actually in number 4, right? But I'm saying, I guess there's a faster, again, there's like a faster way to do it, or a reason why that pattern's there. Now the last thing, just to kind of maybe blow your minds a little bit. We said 1 over 1 minus x is, yeah, 1 plus x squared plus x cubed plus so on. Look at number 5, 1 over 1 minus x quantity squared. So you guys have it on the board over here. The answer is 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus so on, right? How is 1 over 1 minus x quantity squared related to 1 over 1 minus x? Well, one thing you can say is it's the square of it, I guess, but calculus-wise, there's a nice relationship between these two. This is 1 minus x to the minus 1 power. Yeah, in fact, it actually is just the derivative because there's a -1 that pops out. So this is actually the derivative of this. If this is f of x, then this is actually f prime of x. You can check, right? If you differentiate 1 minus x to the -1 power, and you guys were sort of doing that when you were doing those derivatives, right? Like, do you believe that? Okay. Here's what I claim. Differentiate the left-hand side, differentiate the right-hand side. What happens if you differentiate the right-hand side? What do you get? One becomes 0, x becomes 1, x squared becomes x cubed becomes x to the 4th becomes, and there you go, you get the exact same answer. That's from the table. So basically my point is, like, there's a few functions you should know, and then otherwise you should try to bypass the tables and just use it. So basically what I want to say is you can differentiate and actually integrate. This is a big thing. Taylor series, term by term. Actually, the very last thing I'll say is if you think about the relationship between 3 and 4, you guys noticed this in the back over there. You guys noticed that 4 really is the derivative of 3. So if you integrate this term by term, this was the answer to 4, right? You get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. So it's kind of neat. I just think it's cool. Like, it's ways to build new power series from old ones. And it's kind of a new way to get information, like I said, about these derivative, finding the derivative at a point, some higher derivative and something. It's like something that would just be horrible if you try to do it is actually nice. So we'll continue with that next time. There's a few more techniques, and maybe I'll give you some problems to work on, some examples. And that's going to be the big thing. We're almost done. OMG, you guys. What? We're good? Okay, we'll stop. Thank you. I'll post the problem set for Friday. Other things like that. Thanks for those of you on Zoom. Hope you got something out of that. Stop the recording now.